My name is Matthew. I am a software engineer at Facebook, and today I'll be talking about polymorphism with protocols. Now, as an engineer working on a large code base with hundreds of engineers committing code every single day, it can be a little bit challenging, and I wanted to share about one of the most valuable lessons I've learned so far working in such a big code base. So, working on such a big code base, I think one of the most valuable lessons is the ability to think about the need for good API design when you're writing code. And API design affects multiple stakeholders. First of all, your users who use your products and your features, your coworkers who work on the same code base as you, and even yourself. So users come to expect high reliability and stability when you're pushing out new features. And your coworkers want to extend your features, the code base that you architected and maintained. And yourself, you want to be able to fix the urgent bug. So you need to be able to read and understand code that you've written yesterday, but also maybe 3 months ago. And how do we then decide what makes good API design? So I want to talk about 3 characteristics of good API design. I think good API design, firstly, is code that's easy to read and understand, code that is easily testable, and also code that makes it hard to make mistakes. And to do this, we are going to look at a very concrete example. We're going to build some sort of calculator app because there's just enough room in the App Store for one more calculator app. What kind of data structure can we use to express mathematical formulas? I think an easy idea is, well, maybe we can use a tree, something like a binary tree like this. So here we have the leaf nodes that represent numbers, and the intermediate nodes which are operations. In this case, we have the multiplication and addition operator. And those are binary operations that act on our number nodes. What does this look like in code? So here's a first naive approach. I realize the code may be a bit blurry, but the slides will be available after the talk. So we have here a class called node, which represents a node in our tree. And we have the evaluate function that returns the result of the formula, which is a double. We have a couple of properties, and the first property is a value. So this represents the number in a value node, and it's of type double. And next we have 3 properties to represent the operation node. The operation itself, maybe it's an addition or multiplication node, and that's a string. And 2 child nodes, the left and right, for the nodes being acted upon. Is this a reasonable design? Well, I think it's a good first attempt, but there are a couple of observations that I'll talk about that we can actually improve this. First of all, we notice that there are optionals everywhere, and that's because we don't know what kind of node this will be at compile time. If it's in a value node, we might need the first property which represents the value, and we don't need the rest of the 3 properties, and vice versa if it's an operation node. Which of them can be nil? Well, all of them can be nil, or none of them can be nil. And those are invariants that we cannot express with this data structure right now. Should we use structs or classes? And Swift brings us a very rich type system, and we want to experiment using a value type to represent our data model because we can get rid of, we can avoid shared mutable state. And that makes our code easier to reason about. So what happens if we do this? If we grab a node and set its left child to nil, well, if it's a reference type, anything can happen. If it has multiple owners, you can get the values changing under you, and you might not be able to update the UI. But if it's a value type, every instance has its own unique copy of the data, and that makes it easier to reason about. So let's jump into Xcode Playground right now and see how we can improve this situation. So I have a playground right here. I'm just going to make a little bit more room And hopefully this is large enough for you to see. So we have our class, our node class that we talked about earlier with the 4 properties. We have an initializer which does something really simple, and it just assigns the parameters to our properties. And for convenience, we have defaulted them to nil so that you can see that's easier to express our data structure later on. Jumping down, we want to instantiate a version of our tree so that we can actually test what it looks like. Here we have a node that represents the root of the tree. It's an addition node, and as a left child, it has the multiplication node with 2 values, 2 and 3, and the right child with the value of 4. So this represents a formula like 2 times 3 plus 4, which equals 10. And you can see that when we print it out here on the console, we have a value 10. So let's look at how the evaluate function is coded. It's pretty simple. We just look at our operation property, and if it's non-nil, we're going to assume it's an operation node. And because it's an operation node, we're going to insist that we must have a left and right child. So we use the guard syntax here and optional binding to retrieve the values of the left and right child. And if any of them are nil, we're just going to trap. We're just going to terminate the program with the error message. We have a switch statement which we'll decide how we can understand what operation is being performed. And in this case, we're just going to evaluate the children and sum it up for addition operation and multiply them for multiplication operation. If there is no operation in our property, if it's nil, we're going to assume it's a value node. And we're going to try and retrieve the value from the node and trap if there is no value. And we're just simply going to return the value. So that's how we've implemented the evaluate function. So right now, we can see that there are still issues that we talked about, the observations that we mentioned. Let's try and get rid of all the optionals right now. So one way to do this is to introduce an abstract class, to make node an abstract class and have more concrete types that represent the value and operation nodes. So as an abstract class, we don't really need all of these properties up front. Let's see, we're going to get rid of that. And our evaluate function is going to be really simple. We're going to get rid of all this and just trap immediately. So this is what our abstract class looks like. We're going to introduce now our value node again. Oops. So this is what our value node looks like. Notice that we don't have optionals anymore. We have only a single value property. And that's because every value node has a number. We need to, again, re-implement our evaluate function. In this case, we're going to overwrite the function from the abstract class. Oops. Sorry about that. And here we're just going to return the value. So now we need to re-implement our operation node. Oops. So here we have our operation node. We have the 3 properties, and they're non-optional. Every operation node needs to know about the operation being performed and needs to have exactly 2 children. We're going to implement our evaluate function. So in our evaluate function, we're going to switch on the operation same as before. For the plus operation, my snippets are not working. So we're going to just take our left child and then call evaluate on it, and add the right child and call evaluate on it. And we're going to do the same for our multiplication operation. And that should be sufficient to get us going. We're going to replace our abstract types here. So this is now an operation node. And so is this. And we're going to replace our value nodes with the value node type. Fingers crossed. Let's see if we can get the same result as before. And yes, so we see printed in the console, the number 10. So we've come pretty far. We've got rid of a lot of the optionals. We do have a switch statement right here. And if you believe that conditionals are the root of all evil, then we should try to get rid of the switch statement right here. And we can do this by making the operation node an abstract type as well. So let's try to do that. So I got rid of what we had before and reintroduced a simpler version of the operation node with only 2 children and the initializer. And now we need to introduce our addition operation. And we just have to implement evaluate again. And we'll do the same for the multiply operation. And we can now replace the operation node with an addition here. We can get rid of this operation parameter. And the multiply node, getting rid of this multiplication operator. And hopefully that works. And yes, it does. So what have we gained here? We've made our code easier to read and reason about because they're much smaller than before. We've made it easier to test because we can just instantiate a very specific type, for example, the add node, configure its children, and call evaluate in our unit tests. We don't have to conditionally set up the properties and make sure everything works. And it's harder to make mistakes now because we don't, each of these nodes have invariants that we have to satisfy. We don't have to make some properties optional just because. And if you were in Java, this is probably where you might stop. But because we're in Swift, we want to actually really use value types right here. But of course, this is an abstract class, and that's how we implement dynamic runtime behavior with polymorphism. So what we can do if we want to use a value type is then to move towards protocols. So we're going to change our node class and make it a protocol. And being a protocol, we don't have to specify an implementation for our evaluate function. I'm going to change this to a struct here. And we can even get rid of the initializer because Swift synthesizes the initializers and structs for us. I'm going to get rid of overwrite keyword. And again, our second abstract type, we can turn it into a protocol that extends node. And because it's a protocol, the way we specify property requirements is to indicate whether we want a getter or a setter. So we need to specify get in braces to indicate we want a getter. And we can get rid of the initializer again. Turning our addition node into a struct, we need to now to satisfy the protocol requirements on our operation node type. And we can get rid of the overwrite keyword. And we'll do the same for our multiply. Oops. Introducing the protocol requirements again. Sorry, property requirements. And getting rid of our overwrite keyword again. So this should just work. And we see that, yes, we return 10 again. So this is a successful refactor. And now we've moved towards value types, and we can gain all the benefits of using value types over reference types for our data models. One other advantage that we got really easily is the ability to extend this protocol with new functionality. So for example, if all of the above code was in a third-party library, we didn't have any access to the code, in the state that we were before with the switch statement, we will not be able to add new functionality. But because this is now a protocol which we can extend, if you imagine all of the above code being in a separate space and we don't have access to the source, we can still provide new functionality by introducing our new types and conforming to the protocol. So here I have introduced a power node operation which takes a power of 2 numbers. And we're going to just implement the evaluate function here. So what we did was just call pow, which is a function in the standard library. And this raises the left child to the power of the right child. And to test this out really quickly, we're going to add the power node right here. So the left child will be whatever we had before with the value of 10. And the right child we'll introduce a value node with the value of 2. And hopefully this works. You should see the number 100. And we do see that here. So that gives us a lot of flexibility and power in extending what we have. One more thing we might want to do with protocols in Swift, and especially this example, this concrete example of a tree structure, is sort of to visualize the tree structure with an image and something like the diagram that we saw earlier in the slides. So to do this, I've wrote a protocol beforehand called tree renderable. And let's take a look at how we can apply this to our node protocol. So in our tree renderable class, just to visualize what the tree looks like, we need to satisfy a couple of things. We need to satisfy the max height, which tells us the height of the subtree at that node. We need some text to display in a bubble. And we draw each node using a render function that will, in this case, we will implement by calling draw functions to actually draw the nodes on screen. Here we have a protocol extension that satisfies two of the first two, the second and third requirements, text and render. And this provides default implementations. So this is a feature in Swift called protocol extensions that you can use to provide default implementations for certain requirements. And you get that for free by just conforming to the protocol. And in this protocol, we can also call a render to get a UI image. And that's how we can sort of visualize and see what's going on in our tree. So we implement the draw method here by calling, the render method by calling two draw functions, the first of which will draws the current node, and the second one draws children of the node. So let's see how we can pretty quickly get this up and running. So I'm going to provide an extension on node so that we can satisfy the protocol requirements. And to do this, we just need to provide the max height. And for now, I'm just going to return 1 so that we can quickly get rid of the warnings here. So we're going to call a render and see what that looks like. So this returns a UI image. And if we quick look this, we can see that it's just a black dot for now. So and that's because the default implementation of render just draws the current node. And we've said that the subtree is always of height 1. So to correct this, we need to go into our operation node and make a change. Because our operation node is the only kind of node that can have children. So we're going to extend operation node. And we're going to implement max height here. And the height of the operation node is sort of like the height of the children bigger by 1. So we're going to just return the maximum of the left child's height and the right child's height. And we're going to add 1 to that. So if we take a look at our image now, we see that we have a lot more space. But we're not yet rendering the children nodes. So to fix this, we're going to call render. We're going to override render. And call draw, drawing the children. So we're going to pass in the left child first. And this will be to the left of the current node, so just indicating the correct direction. I'll just pass in the context and center so that it knows how to draw that. And we'll do the same for the right child. And then we have to draw ourselves. And now let's take a look at the image that we are rendering. Oops. And then we have a nice binary tree that sort of represents what we saw in the diagram. We're just missing now the text values in the bubbles, and let's quickly fix that. So going to our value node, we're just going to override the text string here. And here we're going to return a string. And what value do we return? We want to return the number that's in the value node. So we're going to use string interpolation. This is a feature of Swift. And we're going to cast our double into int just so it looks a little nicer in the bubble. And we need to do the same for the different operations that we have. So for the addition node, I'm going to return a plus. For the multiplication node, we'll return the asterisk. And for the power node, we're going to return something like a caret. And if we look now at our image, yeah, we have a pretty nice binary tree. So what did we just see? We saw a naive class implementation, which was a first attempt. And we tried to clean it up using polymorphism. We moved into abstract classes. And then we turned them into value types by implementing protocols. We also saw how to implement a third-party protocol, which is to render and visualize our tree using protocol extensions in Swift. If this was an interesting talk to you and you like further readings, I highly recommend Inheritance, Polymorphism, and Testing by Misko. He's the founder of AngularJS, and he talks about this in Java, the context of Java. And the examples in this talk were highly inspired by that talk. If you're interested in API design, I strongly recommend Everyone's an API Designer by John Sandell. He spoke at NS Spain earlier this year. And if you like visualizing trees, check out Playground Quick Look for Binary Trees on Swift Talk. And that's all I've got. Thank you.
Thank you. Okay, hope you all enjoyed the talk. Any questions for him?
Hello. Hi. Yeah, so switching to the protocol for the operation node, you lose, well, it forces you to basically re-implement the left node and right node properties for every implementation, which seems a little bit like verbose if you have a lot of operations. Do you have any thoughts on a workaround for that?
Unfortunately, no, because protocols don't have a concrete implementation. What you specify in the protocol is just a requirement, and you have to satisfy that in your own type.
So something I've used in that situation would be because the difference between them is just the implementation.
Right.
So if you make the evaluate function a property, you could potentially swap that out and just use a struct.
What do you mean by making the evaluate function a property?
So if instead of having a protocol for your operation node, if operation node was just a struct, and then the evaluation was a block, a closure that you could set, and you can kind of make different implementations of that without sort of having different implementations of the protocol, if that makes sense.
Sure, I guess that's one alternative.
Do you kind of have a rule of thumb for when you would use a protocol versus using something like that?
So I guess what you're suggesting with using evaluate as a closure of sorts inside of your type, well, that just hides the implementation detail of having precisely two children. So you'll be able to express that in any way. I mean, you might be able to support like a tertiary or trinary kind of operation as well. Yeah, so to me, it's just a matter of taste. And if this makes it simpler to just understand it as you're only going to deal with binary operations, I think this is just an easy first step.
Okay, thank you.
Okay, any more questions? There are mics at the side. No? Oh, okay. So thank you. Thank you.
Thanks.